It's 8 o'clock in the morning on Sunday, October 1st, 2023, and I've just moved the cows to the fifth cell of the fifth section of the rotation that started on September 15th, 2023. Right now it's about 70 degrees. When I left the house it was 68, but it tends to rise quickly in the morning, so I'm guessing it's about 70. Humidity is a little bit high. Today's forecast is 92 degrees. We're going to get 90s up until, I think, Wednesday. Wednesday we expect an inch of rain. Thursday we expect an inch of rain. Friday, no rain. And then Saturday, a half inch of rain. So it looks like this week we'll be getting some serious rain finally. Hopefully enough to recharge the soil, fill the pond. I don't think it'll fill the pond. The ground is still pretty dry. It's moist. I can put the sticks in fine. It's dry. This area of the pasture is better than the previous area. So let me just kind of point out. So this part right here is like Arizona. And then we get up here and let me just kind of show you. This is pretty typical for this area from east to west. Long grass growing. And somewhat thick. It could be thicker, but it's somewhat thick. So I think that's plenty of forage for the cows. I did catch the cows. They weren't grazing in the last strip I gave them. They're grazing in previous strips, which means that last strip didn't have much for them. There wasn't much reason for them to go back after the initial graze, which is fine. If there's not a lot there, then I would prefer that they kind of stayed off of it and grazed somewhere else. F.E. Gollum has been commenting on my rant about science and stuff. The question that he raises is one of definitions, and honestly, definitions aren't really that important. It's the ideas behind the definitions that are critical. If we fall into the trap where we abstract away the ideas and then use those abstractions to draw conclusions incorrectly, then we're basically wasting our time, right? And so he wants to argue that this is a very popular argument, that a theory is a well-tested or well-proven idea about nature and how it works. And I'm going to contradict that definition by two words: ether theory. Okay, so he's using that definition of theory because the definition of theory that I use in physics is different than his, right? I'm not going to talk about my definition theory. I'm going to talk about his definition theory. So he has this concept called the theory of evolution. And I know this without even talking to him. I know what he's going to say about this. Theory of evolution. The problem is the theory of evolution has been proven wrong, not just once or twice, but many times. All of Darwin's predictions were incorrect, right? Subsequent theorems that were created to address the findings that the theory of evolution was incorrect. So they take the theory of evolution, they modify it, and they call it the theory of evolution, right? That's not confusing at all, right? It is totally confusing, and we would never do such a thing in physics. We would call it the modified theory of evolution, or evolution version 2, to distinguish it from Darwin's original theory, so that when people talk about Darwin's original theory, they can have a conversation without getting confused about what exactly we're talking about, right? So they revised the definition of the theory of evolution to match the data, and then that theory turned out to be incorrect. And so they revised it again, and that theory turned out to be incorrect. And they revised it again, and that theory turned out to be incorrect. So the theory of evolution has a long history of being redefined, so much so that the current definition of evolution, of the theory of evolution, has nothing to do with what Darwin talked about. There's no relation at all, right? And the reason why is pretty simple to see why they're doing that. It's all about politics and religion. They want to go to school and teach the kids about the amazing theory of evolution that is so successful and so wonderful, and everybody uses it in every aspect of their lives. And you have to understand this theory because this theory is the most important thing ever invented, right? And that's what they tell the school kids. And the truth is the theory of evolution is nonsense. It's useless. In fact, it points people in the wrong direction. And it has caused a lot of very, very horrible events in history, right? You could argue, for instance, that Hitler was using the theory of evolution to say that the Aryan race was superior and therefore we have to exterminate the other races, right? You could say that, right? Whether it's true or not, that's a separate matter. But definitely people do say that, that because of his ideas about evolution, he proposed, slaughtering millions of people, right? But certainly in the Soviet Republic, they tried to use the definition of evolution. They came up with their own version of evolution that we call Lamarckian, right? And they tried to use that to govern their agricultural industry, and the end result was mass starvation. So using the theory of evolution that way certainly caused problems. There's other issues too. Famously, there was a scientist really not that long ago. This didn't happen that long ago in history, but he read the Bible, and he noticed that in the Bible, God says that he created creatures after their own kind. And so he looked at the theory of evolution and said, that's nonsense. That contradicts the Bible. It does. There's people out there that try to, compromise and find a theory of evolution that works with the Bible, but they neither understand what the Bible is actually saying, nor do they understand the theory of evolution, right? And so they come up with this theory that contradicts both. It's, completely garbage, right? It's not even correct for either scenario. Anyway, this scientist, he read the Bible, he saw what the Bible said, he believed what the Bible said, and he said that this contradicts the theory of evolution. And so he proposed an experiment, a hypothesis. He had a hypothesis, an idea. He says, if I do this, then this is going to happen. And he carried out the experiment, and the experiment is still occurring to this day. And the experiment proves abiogenesis is nonsense. Abiogenesis is the idea that life can arise from nothing, right? And so he proved definitively. He gave ample opportunity for life to survive. He created a broth that is well known to go sour very quickly because of the nutrients in the broth. And he made this broth inside of a glass vessel that is designed such that air cannot, air can get in and out, but particles in the air can't, right? And so his idea was that the source of infection was little tiny seeds of infection in the air and not from the air itself. And so you can sterilize the air, and you can wash your hands and wash these seeds off of your hand, and you won't get an infection. And indeed, he was correct. And he saved countless lives, and he saves countless lives today. In fact, the field of surgery and medicine would not be possible without his discovery, his experiment that showed that abiogenesis is nonsense, right? Abiogenesis was one of those ideas attached to evolution. Now we all know, of course, life doesn't arise from nothing, that, air molecules bouncing against each other randomly don't create, different kinds of diseases that we might find in our bodies, right? So there's a case where somebody used the Bible as their guide, and they believed the Bible, and the Bible contradicted prevailing theory. I use that word theory to explain what I'm talking about. And in proving the theory was wrong, did the theory become any less of a theory? Is abiogenesis no longer a theory because it was proven wrong? What do we call abiogenesis? Abiogenesis is a what? Now, he wants us to only use the word theory for things that are proven correct. The problem is you can't prove a theory correct. You can only contradict a theory. Right? I can run countless experiments, all of them which comport with the theory, but I have not proven the theory correct because it takes one experiment that contradicts what the theory predicts, and that theory is incorrect. Just one. We can have theories that have survived for countless millennia, and one experiment can cause us to abandon that theory completely. So no theory is safe, right? Again, I show that the word theory doesn't mean some well-tested and well-proven idea. The word theory means it's an idea, okay? Now, the word theory actually comes from mathematics. In mathematics, we start with assumptions, right? They might call those, I forget what they're called. But anyway, they're assumptions. They're basically like, we assume that you can add two numbers together. We assume that you can multiply two numbers together. And then you say, well, according to those two assumptions, we have the distributive law, They call it a law because it applies to lots of different algebras, but really it's a theory. It's a theory that we can prove using logical steps based on those assumptions, right? And so in physics, we do the same thing, right? So we start with a set of assumptions, and then we use logical manipulations to draw a set of conclusions. And that process of using those assumptions, applying the logic, and getting the conclusion, we call that the theory, right? Now, a theory is not tested. It doesn't have to be tested. It can be tested, but it doesn't necessarily have to be tested. In fact, a theory doesn't even have to be proven correct. A theory can be incorrect. The first experiment we run against a theory shows it's incorrect, but it's still a theory, right? It's still a theory. Now, we can go back and look at the assumptions and say, aha, that's your problem. You made the assumption X, when we know now that X is a bad assumption because it leads to bad theories such as yours. So don't use assumption X. Okay. A good example of that is in relativity theory, right? The assumption was that the speed of light is constant for all, or the assumption was that speeds add using the, I want to say Aristotle, but it's not. Let's just say Aristotle. The Aristotle method of adding velocity. So if I'm on a train that's traveling 50 miles per hour and I throw a baseball at 50 miles per hour, then somebody standing outside of the train on the ground will see that baseball move at 100 miles per hour. 50 plus 50 is 100. That's an assumption of how velocities work. And so you can draw a theory out and you can say, well, what happens if I'm on a train that's traveling close to the speed of light and I shoot a laser that's traveling at the speed of light? Would an observer outside see that beam of light traveling at twice the speed of light? And so Einstein used a theory. He said that assumption is bad. Velocities do not add. There's a more complicated formula involved. Okay. And he used as the basis for his theory the assumption that the speed of light is constant everywhere, all the time, for everyone, in any constant frame of reference. If you're not accelerating, the speed of light is constant. It doesn't change. And so for each person, the speed of light has to appear to be the same. And so what we do instead is we bend space and we bend time. And so the person on the ground watching this light, the spaceship shooting by, will see inside the spaceship a person moving in slow motion, because for him time has slowed down. He'll also see the spaceship has contracted in length, right? So he'll see space and time bend, because the assumption was earlier that space and time don't bend, but now we throw out that assumption and we have a new set of assumptions, and so we get new theories. Now the old theories are still theories. Based on those sets of assumptions, they still draw correct. And in fact, we can still use those theories effectively for many different cases that don't involve speeds close to the speed of light. Okay. We can't use those theories for cases where the things are going much faster. There's just a limit to what you can do with the basic theories that draw on these primitive assumptions, right? Okay. Now, my point is this, is the theory is the thing that you come up with in your head. It's an idea. And if you don't like me using the word theory, then use the word idea. Okay. Now your idea can be a complete nonsense. Like I assume trees grow upside down, right? Your theory can be based on assumptions and logical conclusions, right? Let's draw a conclusion. Aristotle is a man. All men have two legs. Therefore, Aristotle has two legs, right? So that's a logical set of steps, right? We use the assumption that Aristotle is a man and all men have two legs, right? If any of those assumptions are wrong, then the theory is wrong, obviously. But if we have that theory and we use the logical steps, and then we find that Aristotle has three legs, then we say, well, where did I go wrong? Did I have bad assumptions? Did I apply the logic incorrectly? Right? Anyway, my point is this, is that certain people within society want to elevate the word theory beyond what it's supposed to be. And I insist upon pooping on the word theory and laughing at it and mocking it. I insist on telling everyone in the world that the beginning of science is the realization that you're wrong about everything. That every idea that you have in your head about the universe and the world around you is incorrect. Okay? I like to tell people, I said, if you're 99% sure of 100 facts, which fact is wrong? Or how many facts are wrong? How do you find that fact? What you have to do is you have to say, well, we have to assume that any of the facts could be wrong, and we have to retest them until we're 99.9% sure. And then I say, well, what if you have 1,000 facts? And then you're 99.9% sure, right? And then so on and so forth, right? And so we're left with things like where a reporter asks a physicist back in the 90s, if you turn on that particle accelerator, will you create black holes? And the physicist is puzzled at the question, and he says, it's certainly possible, right? And then the reporter runs with the story saying that the physicists are going to create a black hole and kill us all, right? You know, and then the physicist is like, no, I said it's possible. That means in the realm of possibilities, it exists as a non-zero possibility. Is it probable? Absolutely not, right? When they set off the nuclear bombs, there was the concern that, hey, you know, there's a possible issue with the nuclear bomb. If we make it hot enough, we can actually ignite nitrogen. We can burn it. And it could cause a chain reaction, and we'll be left with no atmosphere, at least no breathable atmosphere. It's possible. Is it probable? No, absolutely not. Right? Now, thankfully, their theory that you could possibly ignite the atmosphere was an incorrect theory, but it was an idea. It was a proposal based on logical assumptions, right? Then we have, on the opposite end, we have the Higgs boson was being detected, I want to say 5 or 10 years ago. I don't know exactly when it was detected. But so they're running the experiment with the Atlas Muon project, which, you know, I got to have a part in that in my undergrad years. I got to help design and build some of the components, right? I made a small, tiny contribution to it. If you're interested, one day I can sit down and tell you exactly what I did and how insignificant it was. Regardless, I had the privilege of working on that project as an undergrad, and that project detected the Higgs boson. Now, they ran a bunch of experiments, and they had a certain level of confidence that they had found the Higgs boson. But that level of confidence wasn't high enough for the physicists. It's enough to say, hey, I think we have something. Let's run some more experiments in this energy range, right? And so they ran more experiments, and eventually they had enough data that they could say confidently, we know that the Higgs boson exists at this energy level, right? Plus or minus some small number, right? And so they didn't detect it once and say, aha, we found it. They didn't detect it twice and say, aha, we found it. They didn't detect it thousands of times and say, aha, we found it. They had to detect it billions of times. Billions, right? Thousands of millions of times, okay? And only then were they willing to get in front of a microphone and a camera and tell the world, we found the Higgs boson, right? Now, in the back of every physicist's mind is the very, 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 very tiny possibility, improbable possibility that we're wrong, that what we saw wasn't the Higgs boson, or that it was just a random event that happened to coincide. Around the same time we discovered the Higgs boson, there was another bump in the data. And people looked at that bump and they said that bump should not be there. According to theory, that bump shouldn't exist, right? Now, that bump was only seen a few times, like a couple hundred times. And so lots of physicists said, it's nothing, just ignore it, right? It's not going to be anything. But a whole bunch of other physicists, recently out of work because the Higgs boson disproved the theory of supersymmetry. And so all those physicists that were working on supersymmetry, they basically looked for another line of work. A lot of them went to condensed matter physics. But at this point, there's really not a lot happening in the field of particle physics, not like it used to be, right? So a lot of these theorists, these theoretical physicists, and I say that derisively, mockingly, haha, look at the theoretical physicist, he's so funny. Look at him say nonsense, and look at people think that he knows what he's talking about when he doesn't, right? Ha 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 ha, theoretical physicist. I'll explain that in a minute, but the theoretical physicist published multiple papers about that bump saying, oh, this shows a brand new theory that's amazing and wonderful, and hey, you need to give me a bunch of money so we can further research this. Well, because that bump was so interesting and so many papers were published on it, the physicists that were running the particle accelerator decided to zoom in on it, and almost instantly the bump disappeared. It was just random chance, right? So sometimes these bumps you see don't exist, They're just random chance. It just happens to be that a bunch of random variables happen to coincide and produce a bump that doesn't exist, right? So obviously all those theoretical physicists that publish those papers saying like, look what the amazing new physics is based on this bump. I don't know what they're doing. They're probably working at McDonald's or something like that. Okay, last little thing before I stop here. Theoretical physicists versus experimental physicists. There is a huge divide in the physics community. Theoretical physicists are they don't contribute anything to physics. I'm going to say it outright. They don't do anything. They consume all of the airtime. They spout out a lot of nonsense. They create a lot of fiction and fantasy. They create these science fiction scenarios that are certainly wonderful to think about, and could be the topic of a great novel. But in terms of contribution to physics, they do very little, if anything. And I'm using the word very little the way a physicist uses very little, right? I'm not talking like 2 or 3 out of 10. I'm talking 2 or 3 out of 1,000,000, okay? The real physics works happens in a laboratory. It happens with actual devices. It happens with real things happening. Now, the beautiful thing about being an experimental physicist is when you get your results, you know what it could be. You know that it could just be a fluke. You know that it could be the fact that you didn't calibrate your instruments properly. You know, it could be the fact that your physics lab is near a subway station and you happen to turn on the machine right when a subway passed by, right? And so you have to take into account all of these possibilities all of the time. And so when an experimental physicist publishes a paper saying, look at this weird thing I found, okay? They'll often publish papers saying, hey, I found this weird thing, but it's possible that it's just a random fluke, right? They'll publish papers saying, hey, I found this weird thing using this machine I created. I could just be an idiot and I made the machine incorrectly. Could you please try to replicate my results, right? They could be publishing a paper saying like, hey, we've done this experiment countless times. I'm very certain that my machine is calibrated correctly. And I'm showing this new result that contradicts some existing theory. Haha, look at the theoretical physicists, they're wrong yet again, right? And oftentimes they're publishing papers saying that, hey, we saw this new event and we have an idea on what it might be. We want to create or modify the device to see if it actually is that thing or something else, right? And the last category, that happens quite often, right? And that's the exciting thing that experimental physicists like to do. And the nice thing about being an experimental physicist is you get to do the theory before the theoretical physicists do. You get to start working on the theory when you see the first numbers come in, right? Let me give you an example of who should be the most famous physicist of all time, who probably has done more than Newton in the field of physics, right? I feel sorry for Newton because he had a lot of great ideas. The problem is he didn't have the technology to experiment on those ideas, right? You go back to Newton's writings and he was pretty sure that light was a particle, but the evidence that it was a wave was overwhelming, and so he had to basically abandon that idea, right? Anyway, Rutherford, Ernest B. Rutherford, is probably the most influential physicist of all time. To give you an idea on what he did, he came up with, him and his people came up with several iterations of an idea of what the atom actually looks like. Okay? His work was critical to developing quantum mechanics. Quantum mechanics would not exist without his machines and his measurements. And furthermore, he detected basically all of the basic particles that can be detected without, advanced techniques. He not only did that, but his probably the greatest discovery that he made. I'm going to kind of tell the story a little bit. So some of his lab assistants or lab workers or co-workers, I don't know what you would call them, they set up an experiment where they took alpha particles, which they knew how massive the alpha particle were and how fast they travel. They were able to measure that using magnetic fields and all kinds of stuff, right? And so they knew what they were shooting at this piece of gold foil. The gold foil was very thin, extremely thin as you can make anything. And so they shot these alpha particles at the gold foil, and they had a sensor set up on the other side. They're looking for the deflection. And so they measured the deflection, and they went to Ernest Rutherford with the problem. They said, hey, we're not seeing all the particles these particles were being absorbed by the gold, right? Now, Rutherford, who was a great experimental physicist, knew that you can't do that. You can't have, like, the gold foil isn't becoming bigger and bigger. It's not increasing in mass, right? It's still the same piece of gold foil it used to be. And so he said, why don't we set up the detector at the same side as the emitter? And so they did, and they detected all of the particles, and they discovered that lots of the particles were bouncing back towards the emitter, right? And when he saw those results, he immediately knew that the atoms had to have a dense, massive, tiny nucleus. That's the only way those particles could bounce back towards the emitter. And that was the beginning of the modern theory of the atom. And from there, a series of events, and eventually you had Bohr proposing that the reason why electrons aren't falling into the atom is because electrons exist as a wave that interacts with itself, and the wave cannot collapse. It can only sustain itself at certain intervals, at certain quantum leaps that you can count. Quantum means countable. And so the Bohr model of the atom exists even today, and it's an amazing piece of history. So that's, Einstein, yeah, he did some amazing things. Yeah, he's pretty cool. But Rutherford is so much greater than Einstein. He did so much more for physics, and not just theory, but experimental evidence, right? And he was so productive during his life. I don't think we're ever going to see anybody like Ernest B. Rutherford again, right? Maybe one day we'll have a physicist that specializes in building small projects that don't take a lot of money or time. I don't know. I've often had dreams that I'd like to, if I got a massive amount of wealth, I'd, rent some space in the middle of nowhere and hire a bunch of physicists and give them like $100 and say, what can you build with that? I think that would be exciting to give physicists the challenge of what can you build with a limited budget, rather than saying, what can you build with infinite budget? Anyway, I'm neither here nor there. The point remains that theory is just an idea. We shouldn't be modifying theories and saying it's the same theory. It just confuses everyone. We should call it something new. And theories exist to be disproven. They can never be proven. And the beginning of a science, the beginning of a scientist is a person who says, I'm probably wrong about everything. That's where you got to be. You got to be that kind of person that says that everything I think I know is probably wrong. Even myself today, everything I think I know is probably wrong. And it's just a matter of finding out how it's wrong. How do I do that? That's the beginning of science. Anyway, guys, have a great Sunday. Have a great day. Take care and bye-bye.